Hello everyone and welcome into the Platypus Hall in the PyConline AU 2021. I'm Caitlin McLeod, the host for today, and we've got Chris Neugebauer who's about to give our next talk. First off, I just want to do a quick acknowledgement of country for where I'm presenting from. So I'm in Canberra, so I wish to acknowledge the traditional custodians of the land we're meeting on, that I'm presenting on really, the Ngunnawal people. I want to acknowledge their and respect their continuing culture and the contribution they make to the life of this city and this region. And I also want to acknowledge and welcome other Aboriginal and Torres Strait Islander people, as well as other First Nations people from all across the world who may be attending today's event.
Thanks, Caitlin. And I'm presenting from Petaluma in California on the unceded land of the Coast Miwok people.
Great. So yeah, as I mentioned, first off we've got Chris Neugebauer giving a talk called On the Use and Misuse of Decorators. Chris is this is pre-recorded, so he's going to be available to do questions throughout and also after the talk. So if you have questions, chuck them in the chat and in the Q&A view, and we can answer them after the quick talk or give commentary throughout. I think we're good to go. Take it away.
Let's go. Hello there. Thanks. My name's Christopher Neugebauer. You can find me on the internet as ChrisJRN, and this is my talk about decorators. Now, unlike the talks I've given at Python conferences in 2019, 2020, which were kind of trying to investigate pointed questions about the future and the philosophy of Python, but accidentally ended up being all about decorators, this year I'm going to start by discussing decorators and seeing where I end up. In particular, I'm not really interested in discussing ethics, religion, or philosophy. But what I will tell you is this talk will end up relatively basic and will probably not even end up in that place. So that we can cover a lot of ground, I'm also going to skip some irrelevant details. Obviously, if you think a detail was important, well, it was actually irrelevant. I'm sorry about that. I realize I spoke a bit about my last bunch of talks without actually mentioning who I am. These days, my day job is as an engineer at Toolchain. We are the sponsors of the open source Pants developer workflow system, which makes it easier to run your favorite Python tools more efficiently, more effectively. Internally, we use decorators a lot, and I think I'll get to that at the end of this talk. But very first, a recap of what a decorator actually is. So, say you have a function which does something really obvious like print, I am a banana. When you call it, it does the thing that you wrote in the code. It prints, I am a banana. Now decorators, which are these statements which begin with an @ symbol before the definition statement, are Python's way of providing a structured way to do something with functions, methods, or in later versions of Python, classes. Now adding this surprise decorator makes our function print out another thing before it executes. Surprise! And this is how that decorator works. Our decorator takes that function as a parameter, it creates a wrapper function, and then it leaves that wrapper function in the place of the function that we wrote. To be more clear, when we put that decorator statement before the function, once Python defines the function, it passes the code to our decorator, and then the decorator leaves the function, the new function in place of the original function. So in summary, that means that a decorator is a function that takes a function and leaves a function. Except that's not what it is at all. And to show you why, we're going to return to our original decorator. Under the hood, our modern Python decorated function, that's this bit at the top here, is doing the same bit as our more ancient Python decorated function, which is the bit at the bottom. What's going on here is that this bit after the @ symbol, well, that's actually an expression. And when that expression gets evaluated, that expression is equal to a function, which is our decorator. And that decorator gets called, which gives us the function that we were trying to decorate and what we're replacing it with. So if you wanted to add a parameter to the decorator, you do it like this. You actually end up with functions that are nested 3 deep, which is a bit more confusing than those 2 deep functions that we saw earlier because, well, you take a function that takes those parameters that we defined in the decorator statement, and then at the bottom, you return a decorator function. This decorator function will accept a function that's going to be decorated and it will return the wrapper function. And then the wrapper function itself it calls the function that we defined with the decorator statement. It's really confusing, but it's easy enough to remember if you just remember how that Python code translates to the more manual Python code. It kind of almost makes sense. Which means that a decorator is an expression that is a function which itself is a function which returns a function, but that's also not correct. Because you saw in the last slide there, a decorator just literally assigns the result of the decorator function to the name of the function that's passed in. We don't check that that value be a function because Python doesn't do type checking. There's not really any requirement that there be anything returned at all. And this really seems confusing for things that should just be modifying functions, but at least tells us what a decorator is. A decorator is an expression whose value is a function, which takes a function and does something with it. And that's why decorators are hard to define, and quite hard to wrap your head around at first. On the other hand, decorators are weirdly flexible. They unlock a lot of unexpected and useful design patterns in Python that aren't really accessible in any other way. And they all come from that observation that Python doesn't say what a decorator has to do with the code that you chose to decorate. It just does whatever a function can do. And so that's what today's talk is about, that giant pile of question marks. So for the rest of today's talk, we're going to look at why Python got decorators in the first place, and what decorators enabled in popular libraries and frameworks, and we're going to finish with some design patterns that decorators make possible. Enjoy! So, first up, we are going to look at how Python ended up with a feature that is, on the face of it, more complex than it needs to be. Now, Python has always been an object-oriented language, but on the other hand, a lot of people who worked on Python had come from languages like C, and C is very much a not object-oriented language. And what those C developers liked was that it was possible for multiple developers working on different files to be able to name their variables and functions the same thing and not have to worry about consumers accidentally using the wrong function. The Python feature that enables this is called namespaces, and namespaces were, as Tim Peters put it, one honking great idea which Python should do more of. And the way that we did namespaces in the first place was with modules, your file structure. But as we'll see, this is not really enough. Because say that you have a class which pairs a name and an address, Python gives you the ability to create precisely one constructor. And so you make the fields the parameters. Now in practice though, you might want to create an object from a serialized form like a JSON dictionary, or since it was the 1990s, XML or an INI file or something, I don't know what. Now to do this, you'd need to use something called a factory function. A factory function is a function that lives in the module next to the class that you want to instantiate, which does the job of pulling the parameters to the constructor that you're going to call out of the dictionary. And this is not great. We can't namespace things intuitively and automatically. It's only really the name of the function that makes it clear what we're going to get from the factory function. And just like C, we need to use long, redundant, non-clashing names to make sure that we have uniqueness. Because if we have more than one class in the same module, we need to make sure the names of the corresponding factory functions don't clash. And this is a code organization nightmare, and exactly why namespaces are a honking great idea. And this being the late 1990s and early 2000s, Python looked to the world's source of inspiration on code organization, which was Java. Now, Java has very firm ideas about how code should be organized. And one thing it allows that Python would never allow was multiple constructors. No, never that for Python. But there was one thing that Python could borrow. Java has this concept of a static method, which is a method that gets called on the class itself rather than on an instance of the class. And it has this as a first-class language feature. And one thing that it allows you to do is to organize factory methods underneath the class where they logically belong. And this would have been something that was really nice to have in Python. And so when Python 2.2 was released, it added a fancy new feature. You could define a method inside a class, and then after you defined it, you would call it a class method. And then when you wanted to call that class method, you'd actually call it on the class itself rather than an instance of the class. A class method and static method were two ways that Python decided to do more namespacing. And this way of defining something as a class method without using a new language feature to do it is called the decorate pattern. And with the decorate pattern, people were really happy that they could namespace their code. Now that pattern that we saw, by the way, that's something I'm going to come back to a lot in today's talk. I'm going to call it define, consume, throw away. And define, consume, throw away is an anti-pattern in most languages, but it's something that we reluctantly accept in Python. Now, as I was saying, very, very quickly, Pythonistas discovered a problem with this post-decorate pattern. Say if you have a really, really long method, so long that it goes off the end of your screen, then it becomes really difficult to notice that the method that you defined is actually a class method. And this is a case where it became quite difficult to read Python code and understand what it was doing just at a glance. And so very quickly they decided to do something about that. PEP 318, with the catchy name Decorators for Functions and Methods, came up with some goals for inventing a new language feature to make decoration easier to approach. And it's an interesting read historically because it covers some of the thinking around Python at that time. There's this idea that there might be a JIT compiler at some point and we should optimize for that. But most importantly, they pointed out that decoration was hidden and it should be moved from the end of where it's hidden to the top of the function where it's more in your face. Now, decorators, as it turned out, turned into a really interesting feature in Python. It took class method and static method from being something that was awkward into something that was really easy to use, and it started making more ideas in Python more accessible. So one idea of object-oriented programming is encapsulation, which is the idea that a class has ultimate responsibility for its data. In Java land, the way to ensure that data is controlled is to make sure the data fields themselves are private, and then we gate their access using a method. Then if you need to change an implementation detail, you change in the method, callers are taken care of. But there's also no real difference between a stored property like filling here, that's where you just return the value, and a synthetic property, which is where you calculate something and return that. Now, because Python never really had private fields, it never really discouraged people from directly accessing fields in objects. And by convention, that meant a visible difference between the stored property, which is filling, and the synthetic property. One you call, one you don't. And it made it hard for library authors to change from a stored property to a synthetic property. So Python invented a decorator called property, which came around the same time as class method and static method, but it was even more awkward to use, and so people didn't really use it. But with property, you can start a class that has some stored properties and some getter methods, and by replacing the getter method with a property, well, now you can access the synthetic property and the stored property in exactly the same way. And it lets you refactor from a stored to a synthetic property without breaking compatibility. Now you don't need to call awkward setter and getter methods, nor do you need to know if a property is stored or synthetic. Now, even though it changes the semantics of those methods that we've defined, it's clear to the calling context what to do. Now, that decorator syntax meant that properties caught on immediately in Python, and plenty of languages have stolen it since. Properties are an interesting case because unlike the decorators that we started off showing, there doesn't actually need to be any wrapping going on behind the scenes. In Python's case, property works by adding some magic inside the internals of classes. Here in the getAttribute method, we intercept an attribute lookup. The decorator just needs to do enough to tell subsequent calls to getAttribute that this is a property and you should do that property thing. And this is really all you need to do. Python's implementation is a lot more complex, but the seeds are there. You add the interception code into getAttribute, and then you add this decorator at the top to leave the information for getAttribute to intercept. And our new decorator has the same basic effect as Python's property getters. So decorators and Python's model where you can access the internals of a lot of parts of the language mean that you can really alter the semantics of the language to make your libraries easier to use or more powerful. And that's meant that decorators have been used in a lot of interesting places throughout the Python ecosystem. For example, the functools module in the standard library is full of decorators that you might find interesting. But I think it's worth calling out Django in particular because it realized there's a lot of really useful, decorators are a really useful way to apply frequently reused code to functions. Django uses decorators as behavior modifiers for views. For example, require HTTP methods tells Django which HTTP methods are acceptable for a given view, which saves you from having to remember to write this boilerplate down here during the function. And Django uses decorators all over the place. It's kind of made this observation that sometimes there are structured, repetitive behaviors that fit into the pre-call and the post-call parts of a function, which are much better suited to wrapping than they are to using mix-ins or other object-oriented behavior. So we've seen why decorators happened, what things they brought into the world of Python. We've seen post-processing, we've seen techniques for code reuse, we've seen ways to selectively add improved semantics without needing to add new language features. But these aren't the only things that decorators let you do. I want to show you how decorators open up a way to solve problems that other languages have solved with features like anonymous blocks. Some of these things I've talked and thought about in the past, some of these are new. What I'm not convinced about is that any of these are good ideas, only that these are things that are pretty cool. Maybe you should try them, see if they're useful to you. Then we'll find out if they're good. The first pattern I want to talk about is this idea of a scoped block, which is something I touched on in my 2019 talk on anonymous blocks. I didn't have a good solution at the time. Now I do. One of the things that blocks helps out with is maintaining variable scope, so any given block of code doesn't depend on variables that are defined on an inner block of code. And my thinking on this came around from my time working in Kotlin, which has this philosophy that everything is an expression. So if you have a web framework that needs to produce a user response or an error response, you only really need to assign this response variable once. If it's a user, response gets assigned the user response. If it's an error, it's assigned the error response. And this looks reasonable in Python when you don't need to deal with error handling. But once you start to handle the error, well, then you have to define this response variable inside two different inner blocks and handle it in the outer block. It's not very nice, it's easy to make mistakes, and there's a whole pile of Python tools that just don't like this pattern of code. And one way to refactor this is to pull that if statement out as a function, which now has the same structure as the one that doesn't have error handling. But now you need to divert your gaze to a different function to see the inner behavior, which is bad visual locality. It also gives you a new visible function that you may need to support, even though you only intended it as a one-off. The alternative is to put the throwaway function inside the original function, which is better for visual locality. You don't even need to pass a parameter in anymore. But what's more annoying is this define, consume, throwaway behavior. You're writing this function just so you can call it once, keep the result, and that's not clear at a glance until you read the entire body of the function. You know that sometime the code is going to get called, but not when. And this is something a decorator can solve. And this is that decorator. It's called run. And all it does is call the function we're decorating and stores its result. So you can define a function that takes no parameters and returns a thing that you want stored to a variable, like this string hello world. You put the run decorator before the function, and then magically you end up with a variable called hello world instead of a function called hello world. And this is useful for our branching block that we were looking at earlier, because we can go from using define, consume, throw away to defining our variable by using the run decorator here. And this gives us the advantage of scoping our variables properly if we have them. We can define them at the level where they'll be used. We get the scoping benefits of a single use function, but without the poor visual locality of define, consume, throw away, which is really, really nice. The next thing I want to look at is the idea of stream transformations, which is something Python is actually quite good at already, except if one of the transformations you want to do needs multiple lines of code to write effectively. Python has, for the longest time, avoided having multi-line lambdas, and this pattern is one that lets you take advantage of multi-line lambdas. A stream transformation is something along the lines of a list comprehension or a generator expression. List comprehensions, generator expressions, they make a lot of sense when you only call a single method or a single function on your iterable items, or if you can string from one transformation to another with minimal branching. But if you want to do something that requires a bit of branching, well, that's when things get awkward. You have to return to define, consume, throw away, the anti-pattern, which we know by now it's just really not very good. Especially since other languages, including Kotlin, Swift, some others, have really begun to figure this out. If you have a lambda expression as the last argument inside parentheses, you can actually pull that lambda outside of the parentheses. And combined with Kotlin's if expressions, well, you end up with something quite elegant here. Now, we can't really get this list comprehension here into a nicer syntax for this, but we may be able to do something with Python's legacy map or filter functions, those old style transformation functions. Now, previously we would define our multi-line function here, and then we'd call map with the multi-line parameter as a multi-line function as a parameter, which is define, consume, throw away. Now let's use a decorator to get that map call up the front so that it's clear that we're defining a parameter to map. To do that, we need a decorator called apply. Apply takes a transform function like map or filter and an iterable and then accepts a multi-line function as the thing that does the transform on each element. And you use it like this. You say apply map to items using the function that we're about to define and store it to the function's name. With that, we can take our define, consume, throw away code and turn it into something where we say what we're going to do with the code before we define it. It's exactly the same way we would do this with a single line lambda expression. So we've effectively unlocked multi-line lambdas here, which is nice. So that's a couple of patterns where you can use decorators to avoid define, consume, throw away anti-patterns with multi-line functions. Now I want to talk about the builder pattern, which is actually well established in the Python community, but we use it in a really, really ugly way. In Python, we like writing data structures in code, but there's only support for a small number of officially blessed structure types. Builders, on the other hand, are a way to create data structures in a way that isn't restricted to what the language provides. But in its usual form, there's a lot of repetition and there's this side problem of defining the thing, but not showing how it's going to be consumed until much later. And indeed, the first things that you define here are often the last things that you consume. And this is not so much an issue in this reasonably flat data structure, but as you start to get more nested, the lack of clear visual locality becomes difficult. But generally speaking, builders are almost always used like this. You create the builder, then you do things with the builder, and then you build the builder. So we can do that to build up a data structure like an HTML document, but with a slight twist. This HTML node builder class takes a tag name when we create it, and it has a build method that puts everything together at the end. What's interesting is the node method. It's actually a decorator that creates a builder, passes it to the function that we're decorating, and then builds the builder once that function that we're decorating returns. Now, if we just create one more decorator to string everything together, create that initial builder, and then suddenly you end up with a function that defines an HTML document. But more importantly, this function sort of has the structure of the document that we're creating. It strips out all those repetitive calls to builder and just to build the builder, and it leaves us just with the task of doing the building stuff, the adding things to the structure. Unlike our previous patterns, this one encourages you to write more functions, but in doing so, you end up with code where you interact with so much less boilerplate. The final pattern I want to show is one I call the code registry. Unlike previous ideas, which are really geared towards structuring single-use functions in a nicer way, this one is about separating the idea of how you define your code from how you call it. The example I want to show is an idea for a library for handling text processing pipelines. Say you want to figure out what the most frequent word in the Zenith Python is. Well, you can do that with Unix pipelines like this, and you'll get a result, sure. Now, to do this task in Unix, you need to know what all these different Unix commands are which do things and in which order to call them to transform the stream appropriately, like tokenize the words, strip the punctuation, normalize into lowercase, and so on. Doing this in Python really isn't much better. The code's a lot more explicit, but it's a lot more verbose. You need to find a lot more libraries. What would be cool is if I could ask Python to give me a result of a particular type with particular characteristics, say list of instance strings, which is made up of lowercase words with no punctuation and represents word frequency in ascending order. So we've got an idea. How do we turn that into reality? Well, if we use a code registry, which is a class with a decorator in it, which associates a function that we're decorating with an input scheme and with an output scheme, in this case, the decorator just returns the function that we decorated. We don't even wrap it. but we do put it away for safekeeping inside the code registry so that we can find it based on the information we've associated it with. And with the registry, we can define these small functions that represent all of the steps in transforming our data. We can say we have a function that accepts an iterable of strings with some attributes and returns a counter with the same attributes as well as the frequency attribute. And you can define a whole bunch of rules like this, which handle small parts of our text processing. And once you've done that, you can make a function called findSteps, which figures out how to get from an input type with attributes and produce an output type with attributes. And then you can write a function that finds those steps and then applies those steps, and that will do the processing you want. If you've ever written code in Prolog, this is basically the same thing. So this idea of separating the act of calling your code from the place where you define it, it's really powerful and it shows up in a lot of places. In Flask, for example, the app router is a registry that you populate with decorators. The root decorators let you specify the circumstances in which a response-giving function gets called. And closest to home for me is how it's used in Pants. Pants uses a rule registry to figure out how to get from a set of source artifacts to a shippable artifact, so that a developer tool workflow can be defined as a series of small steps, and then the engine will figure out what steps can get you from start to finish. And more importantly, third-party developers can provide their own rules, which helps Pants figure out how to deal with different sorts of artifacts. Pants can figure out how to run those rules automatically thanks to its rule registry. And this is a really nice, unintrusive way to handle plugins. And finally, I want to point out that even though this approach separates the idea of the name of a function to how it gets called, this decorator still returns the original function unaltered, which means you can call the function to directly unit test it. And that's the end of our whirlwind tour. We've seen that decorators have allowed in Python, and we looked at 4 design patterns that show some unexplored ideas that are enabled by decorators. The first being the idea of throwaway functions. They're not truly anonymous blocks in the way that other languages offer them, but decorators are definitely the closest thing we have, and a lot of the patterns that other languages use with anonymous blocks can be approached with decorators in this way. We also saw that decorators are great for transforming functions into the data that they produce, which is useful for programmatically building up data structures. And we saw how the complicated builder pattern is replaced with something that's a bit more readable and easier to nest. And we saw with code registries that decorators allow you to associate functions with a purpose rather than with a name, which means you can call code based on the data you have rather than the name of the function. And that's it. Thank you all for coming along. If you have any questions, you can email me at the address on your screen. There's also a Twitter handle there somewhere. I'm going to be in the hallway track after this talk for questions, and I'm looking forward to talking to all of you then. If you're after code snippets, I will be sharing them after this talk on my website at chrisjrn.com. Finally, thanks to everyone at PyConline AU who made this happen. I'm sad we didn't get to meet together in person again. I also want to thank all of you for coming along to my talk. Hope you've learned something, and I'm really looking forward to hearing some of the questions that you've got. Thank you, and see you next year, hopefully in person, hopefully. Thank you.